You have seen the A-10 at every air show, the low pass, slower than anything else in the sky, and then a beat after it has gone, the sound arrives. A tearing burst that lasts less than 2 seconds. You know the plane. You know the gun is big. Here is what the airshow pass does not show you. The A-10 is not an aircraft that carries a gun. It is a gun that happens to have an aircraft built around it. When ground crews remove it for maintenance, the entire aircraft has to be propped up on a jack stand to keep it from tipping backward onto its tail. The gun has 7 barrels. Only one is discharging at any given instant. That one barrel, the firing line, has to sit on the exact center line of the aircraft. Not approximately, precisely. The entire offset mounting exists for one reason: to put that single active barrel in exactly the right place. The reason it has to sit dead center is a recoil number so large that engineers had to redesign the entire front of the aircraft around it. What you are about to learn is one piece of a larger investigation into the hidden engineering that shapes modern military technology. If that is what you want more of, you know what to do. The A-10 story begins in Vietnam. Close air support, protecting ground troops against armor from low altitude, was failing. The F-100 Super Sabre and A-1 Sky Raider were pressed into a job they were not designed for. In June of 1967, the Six-Day War showed Western planners what they would face: massed Soviet armor moving fast across open terrain. Stopping that from the air with unguided ordnance was nearly impossible. On November 16, 1970, the Air Force issued the AX requirement with a 30mm rotary cannon made mandatory. 4 companies competed for the gun. GE won in 1973 with the GAU-8 Avenger. Fairchild Republic won the airframe competition the same year. Their engineers did not ask where to put the gun. They asked what the gun needed, then built the aircraft around it. The nose gear is in the wrong place because the gun demanded the right place. The number the engineers solved for was 10,000 pounds force, the recoil of the GAU-8 firing at maximum rate. This is not an abstraction. The A-10's 2 TF-34 turbofan engines each produce 9,065 pounds of thrust. When the GAU-8 fires at full capacity, 3,900 rounds per minute, 65 rounds every second, the gun pushes backward on the airframe with more force than one complete engine pushes forward. The weapon generates more backward force than half the aircraft's total propulsion. This is why the firing line matters. The gun body has 7 barrels arranged in a rotating cylinder. As the cylinder turns, each barrel cycles through its sequence: load, fire, extract. The actual discharge happens at one specific point in the rotation, when the barrel reaches the 9 o'clock position as viewed from the front of the aircraft. That position is precisely the aircraft's lateral center line. The gun body itself sits to the left, offset toward the port side, so that at the exact moment of firing, the active barrel aligns with the line running through the aircraft's center of mass. All 10,000 pounds of recoil force push straight back along that line, rather than creating a sideways torque that would yaw the aircraft off target during the burst. There is also a vertical component. The firing barrel sits just below the aircraft's center of gravity, which means each discharge introduces a slight nose-down pitch moment. Fairchild's engineers built a stability augmentation system that engages automatically when the trigger is pulled, counteracting that tendency and keeping the gun sight locked on target. It can be switched off deliberately by a pilot who wants to walk rounds across a wide area, rather than concentrate them on a single point. Everything was anticipated. The firing line is not where the gun is, it is where the gun becomes the aircraft's primary control authority. When the GAU-8 fires, it produces an enormous volume of combustion gas. That gas, oxygen depleted, hot and expanding at high velocity, can be drawn directly into the TF-34 engines mounted above and behind the gun on the rear fuselage. Early test firing caused the engines to flame out. Pilots described it as the aircraft going silent at the exact moment the gun stopped firing. Engineers spent years solving this problem. The muzzle geometry of the firing position directs the blast downward and away from the engine intakes. The ejected casings are collected internally rather than expelled overboard, a system requiring simultaneous feed paths for live ammunition moving forward to the firing chamber and spent cases moving backward toward collection. The casings themselves are aluminum alloy instead of traditional brass or steel. This single material change added 30% more ammunition capacity for the same weight, because aluminum is so much lighter than the metals used in conventional artillery. Every gram mattered because the gun and its ammunition drum already account for 16% of the aircraft's unloaded weight. Every pound saved in the ammunition system meant additional fuel or armor elsewhere. The armor-piercing round needed a penetrator dense and hard enough to punch through Soviet tank armor at operational range. Tungsten was the obvious choice. It is extremely dense, it is hard, and it had been used in penetrators before. But in the 1970s, the majority of the world's tungsten supply was controlled by two countries, China and the Soviet Union. Designing NATO's primary anti-armor weapon around material that would be sourced from the two nations most likely to be on the opposing side was a strategic vulnerability the Air Force was not willing to accept. The United States had enormous stockpiles of depleted uranium, a byproduct of the uranium enrichment process for nuclear reactors. Depleted uranium is approximately 68% denser than lead and about 1.5 times denser than steel. It is also pyrophoric. On impact with a hard target, fragments ignite spontaneously. Unlike tungsten, which mushrooms and flattens on impact, depleted uranium is self-sharpening. As a depleted uranium penetrator drives into armor, the leading edge sheds material in a way that continuously reforms a sharp point, improving penetration as it goes deeper. Depleted uranium penetrators are roughly 20% more effective than equivalent tungsten rounds against the same armor. The firing line sends a 395-gram uranium penetrator downrange at approximately 1,000 meters per second. Here is the detail that even people who know the A-10 rarely notice. The nose landing gear is not simply offset to the right of center, it retracts in the wrong direction. Standard aircraft nose gear folds backward, away from the nose, retracting into a bay beneath the forward fuselage. The A-10 nose gear folds forward into the nose cone, directly alongside the gun. The conventional retraction path was physically blocked by the GAU-8A assembly and its ammunition drum, which extends so far forward that there was no space for the gear to retract backward. The gear had to be completely re-engineered to retract in a direction no standard aircraft uses, because the gun owned the entire center of the fuselage. The firing line determined not just where the aircraft shoots, it determined where it lands and how the landing gear must function to get it there. The A-10 pilot flying that airshow pass, flying the low pass, making the low-level pass, flying the aircraft you recognize is controlling an aircraft where every single anomaly, every visible oddity traces back to one design sequence that began with a recoil force and worked outward from there. The offset gun body, the displaced landing gear mounted in the wrong direction, the engines mounted high on the rear fuselage instead of flush under the wings, the ammunition drum that runs almost the full length of the forward fuselage, all of it radiates outward from a firing line that had to sit in one exact place. Most aircraft are designed and then armed. You start with a fuselage, you design lift, you add propulsion, and then you ask, where can we put the weapon? The A-10 was armed and then designed. The engineers at Fairchild Republic drew a firing line through the center of the aircraft and then built everything else in its shadow. The landing gear is where it is because the firing line demanded it. The engines are where they are because the firing line demanded it. The aircraft tips over without the gun, not because the gun is heavy, but because the aircraft's center of balance was calculated with the gun present from the first drawing. The firing line runs through the whole aircraft, not just the barrel rotating through 9 o'clock, but every engineering decision made around it.